All right, so we're going to talk about graphical solutions. We have a couple ways to solve problems right now, all right? If I give you these two equations, I say solve, and I say any method, what are the two ways we can solve two equations with two unknowns?
Substitution and elimination.
Substitution and elimination. So I can do elimination here on the left side, and I can say, hey, I take the A equation and the B equation, and I'm going to multiply the bottom equation by -1. If I do that, the x's cancel. I get 2y minus y is y. 1 plus 1 is 2. If y is 2, I plug in, I get x is 3. So I have a 0.3 comma 2. The other method is substitution. If I solve for y in B by moving x to the other side, opposite sign, I can get y equals x minus 1. That is what I call B prime. We've changed B, right? But then you put B prime into A, you solve for this, you get x is 3, you solve for y. Doesn't matter which method you use. You end up with a 0.32. But if I take these same two equations and I draw them up here, all right? These are the same two equations. I can take these equations, all right, and I can solve them for y, all right? If I take the top equation here and I say, hey, negative x plus 2y, I can move x to the other side, and if I have 2y equals x plus 1, I can divide everything by 2. And I get a formula of y equals 1/2 x plus 1/2. Great. I can do the same thing on this other bottom equation. I can move x to the other side. This is solving for y. I get equation B, y equals x minus 1. From A and B, and remember we use little letters to denote lines, okay? A and B. I can make a data table, right? Select x, plug in y. We've graphed lots of lines. And if I take this and I make line A green, 0 and 1/2, I don't want to plot that because it's a rational number, not an integer. 1, 1, I can plot 1, 1 pretty easy. 3, 2, I can plot that pretty easy. I happen to know the pattern here. Again, if I draw that line, and that's line A. Over on the other side, I can graph for this. 0, -1, 1, 0, 2, 1. I can plot all those points. 0, -1, 1, 0, 2, 1, 3, 2. And these lines intersect. And what I wanted you to catch is if you look at the graph where they intersect, that point is 3, 2. And that's the intersection of those two lines. But I want you to be clear. It didn't matter which way we did this. 3, 2 was the answer for elimination, substitution, or graphing. All right? There are 3 ways to solve problems. We can always graph 2 lines. All right? And what we're going to start doing, and the reason this works whether it's linear or not. A linear relationship is simply that this is a line. All right? These are 2 linear lines because what's the root part of linear is line. And when you have 2 lines that cross at a point, you can have the solution. That point makes both equations true. And you can see it popped up on both charts, right? So, what if I had 2 lines like this? Y equals x minus 1 and y equals -2x plus 5. All right. If I have 2 lines like this and I want to graph them, now hopefully you guys are starting to notice there's always a pattern in this, and this is what we're going to start talking about. I won't have to do tables very much longer. All right? So if I graph this line in blue, I plug in 0, it's -1. I plug in 1, it's 0. I plug in 2, it's 1. There's a pattern happening there. Every time I increase x1, y increases 1. I plot those points. And again, do you see how the pattern just, you can see the pattern. I'm just doing the dots on the pattern line. There's my blue line. If I do the other one in green, plug in 0, I get 5. Plug in 1, I get 3. Plug in 2, I get 1. Here the pattern is I increase 1, the other one decreases 2. So here we go, 0, 5. 1, 3. 2, 1. Haha. 3, negative 1. Not exactly straight. But again, where do the lines intersect?
3, 1.
Nope.
Or 2.
2, 1. And again, look at your charts. What point's exactly the same on both graphs? 2, 1. If we solve this using elimination or substitution, we'll get the same answer every single time. All right? When you're asked to do graphical methods, remember, label your x and y axes. You should label them on the right and the up. I'm not too picky about that, but try to label them there. Every time we do this, you'll come up with a graphical answer. This point makes both equations true. In the real world, this could be amount of money spent, and this could be return on assets. All right? And there's a magic point where spending your money and return cross that you probably want to do. Spending any more money doesn't help you. Spending less money doesn't give you a full return. There's graphs like that in the world we can do all day long. We're going to spend our time working on just graphing these and getting a point of intersection to start with, and then we'll start working in methods.